all I want to do today is get us set for this next section and stuff you've already seen. Oh, let me make sure the audio is running. Now, let's see. I'm going to put this on. Come on. What's wrong with you? What's going on here? It's my phone. There it goes. As soon as I hear myself through this thing. Okay. I'm good. I should have taken a picture the other day, but when I stream from the house, I have this arrangement. Hang on. In which I do something strange like this. I have a wall, I have another wall, and in the room I have these lights that hang, and we'll just make it one light. So let's say I'm hanging one light right here, and these things are maybe 50 pounds. And then it's attached to a string that connects to both walls. And technically, I make them so that they're the same level. I measured them from the top of the ceiling. So next time I'll bring you a picture of this. So what I'm going to do is I'm going to go ahead and arrange this in a better view. And so next time we'll actually calculate the real numbers that I have there. But here, let me make it look a little bit better by giving, say this is the X direction and this is the Y direction. And I got one connection here and one connection here. So this location would be about X, it's about 10 foot. So I'm just going to say use feet as the, and I'm going to say, I have a clamp and then I have a rope below it, but I'm going to make that instead like a little circle here, and it'll be a weight hanging off the bottom. And so this is tied to the rope so it won't slide. And I'll show you next time how it's done, but let's imagine that this is a ring and it's tied to here and it's tied to here. Now, what's interesting is, I have this in a sailor's knot tied real tight between these 2 points. But if you tie it tighter and tighter, the tighter that rope is, this moves up more and more. You can imagine it's really, really tight. It moves closer to the ceiling. So what we're going to do is we're going to use the next section in statics and figure out approximately the tension in this rope, because that's the whole point of this next section. I would say, at first I said that would be 50 pounds, but this is probably more like 10 pounds. Each one of these lights is about 10 pounds. Technically, I have 2 of them, so what I'll do is I'll measure them next time and we'll take a real look at them. I'll say this thing is dropping down, I'll just say 2 feet. Now that's dropping down probably a foot more than what it actually is. And what I want to know now.
That's dropping down.
Yeah, from this. Yeah, so it's dropping down about 2 foot. So it's kind of dropped 2 foot. Now at the house, it's more like 1 foot. But 1 foot There may be another 1 in this calculation, so I don't want to mess with that. Since this is 10 foot, I'm going to say this thing, and I don't have it in the middle, so I'm going to say this is 4 foot. And the next thing they'll do is they'll label, I guess I'll label this A, this point B, C, and D. What they generally do in these books, now, depending on the book, some of them may say the force in cable AD and stuff like that, but I like to use the tension. So I'll say I want to know the tension in BD. I want to know the tension in AB. And I want to know the tension in BC. And I don't have any more ropes. That's all I got. So, okay, I guess I got to scroll. Yeah. So, how do we do that and what do we do? Well, first thing we do is we kind of focus on this area right here. And so, because that's where all the cables converge. So I'm going to redraw that down, and I have to use the little mouse scroll. And I'm going to try to make it a little bigger. Here's point B. This is the tension in BD. Okay, BC is over to the left, and it points up at a little higher rate. And these are not to scale. So that, you know, tension BC, and then the tension in the rope AB. Now, from looking at this bottom, you can figure that tension in AB really quick. That's just 10 pounds. If you feel uncomfortable about that, and the book has the ways to do that, they'll say, here, I'll split the cable. I have a weight equaling to 10 pounds. What happened to my phone screen? Hang on just a second. Let me get this back. For some reason it cut off. Or maybe I cut it off. And I don't want to echo, so I'll cut the volume down. And maybe it'll show up. Gosh. Oh, here we go. So that tells you, okay, now what the book will do is they'll come in and say, well, this is tension AB. Now what they'll do is they'll focus right here on this, and then they'll set up, and I'm going to do it officially the way they do. Sum of the forces in the y direction have to equal 0 for no movement, i.e. statics, which that's kind of the name of the course. So this means that, and what they do is they say, well, you have to designate which way is positive. So this equation should be AB minus the weight is equal to 0. TAB being positive, the weight being negative. And so it just tells you that this is 10 pounds. So, I mean, it's just kind of straightforward like that. But in the book, what they'll do is they'll take that, initially, they take that section and do it. Later on, they don't. But for right now, that's what we're going to do. So now that I have this, okay, how do I do this? I'll shrink it down, do Alt. I'll just grab this, move it out of the way, and then I'm going to go back and work on this. So we're okay with this. We're okay that this 10 pounds came from here. So at that point, I'm going to zoom back in. and work on this problem itself. Okay, this is not a touch screen. Now, the key here is the angles. Okay, so if I were to look at this thing and say, what angle is this operating on? Well, okay, so I'll go up to the original drawing and say, okay, it's 6 foot here, and it's 2 foot here. So this has to be a 6 by 2 by, okay, looks weird, but it's not a 3, 4, 5. But this is, if it was a 3, 4, 5, it would look like that. So that's the length of this. Does that make sense? Okay, so now, and I have this going on at the house, so I'm making this exactly as it is, except my dimensions are not the same. And I should have done this yesterday, but over here, this is 4 foot across and 2 foot up. So that means this upper length is 2 squared plus 4 squared, square root. Now, let me kind of give you what they do in the book. Sometimes they'll, TBD, they may have something like this, 3, 4, 5. Well, yeah, 5 is equal to the square root of 3 squared plus 4 squared. That's great, but I don't have that beautiful triangle set up here. And so I've got something different. And that's the reason, you could force a 3, 4, 5, but, life doesn't revolve around a 3, 4, 5 triangle. So, what am I supposed to do with all this junk? And that's the key. If you take a look at this, what am I supposed to do? Well, you've got an X plane and you got a Y plane. Not a plane, a direction, sorry. You got an X and you've got a Y. So you got 2 dimensions. So what you do is you sum the forces in the X equals 0, meaning it's not moving this little bolt thing right here, not moving up or down. Left or right. And it's not moving up and down. It's that simple. So then what do? Well, you don't do it that way. How do you do it? You scroll down with the, okay. Well, what I do is look at each one of these. So I'll say sum, what happened here? Now I'm in a text thing, okay. Get back to here. So I'll sum the forces in the X direction. Well, first of all, that one has no component in the X direction. This one does, and that one does. So they both have to equal 0. So I'll say to the right, I'm going to make it positive. So whatever's positive is to the right. Well, that's going to be positive. This one's going to be negative. So I've got T, B, D. But the X component is 6 divided by that. I don't know what that number is, but I'm just going to write it down that way. So that number is just the ratio of those. And that's in a positive direction, but this one is in the negative direction. And that's why I put the minus sign there with a funny thing on the top. Okay, T, B, C is going to the left, and its ratio is 4 divided by this is the percentage, I guess you could say, of it going 4 squared plus 2 squared. So again, 4 squared and 2 squared, I don't know what that is. I'm going to bring up MATLAB. I'll go ahead and do that now. And then I'll use it in a minute. Because I'm going to put the other equation up there and then we'll use it. Okay, hurry on. Okay, so there it is. We'll use it in a minute. Okay, so now let's go back to the drawing. Okay, so I actually have one equation here. It's not really solvable. I can find out TBC as a ratio of TBD. But I can't find TBD or TBC. I can find the ratio between the two. I can't do anything else past that. So I scroll down a little bit more, and then I do this. Sum of the forces in the y direction equals 0, and I'll make that being positive. Okay, so first thing is I got a negative 10 pounds right there. Negative 10. And this is positive it's going up, and this one's going up. So both of those are going up. But the ratio on this TBD is 2 over that. 2 over square root of 6 squared plus 2 squared, TBD. And then the other one's going up as well, and its ratio is 2 over that. 2 over square root 2 squared plus 4 squared, TBC. And believe it or not, there's my two equations and there's my two unknowns. Okay, so I could do these in a variety of ways. But there's something interesting that occurs here. I can't scroll down anymore, but I'm going to turn around and rewrite these equations 2 more times. The first time I'm going to copy them down, kind of arrange them and line them up. The second time I'm going to copy them into a matrix form. And then what I'm going to do is look at the components in there, which is what they don't do in the textbook. But what you'll find out is if you look at the components, there's something that happens to these components that always happens to these components, regardless of whether it's 2D or 3D. So this is the reason I want to take extra time doing this and spend this time kind of, okay, it is going down. Okay, so I'm going to line this up. Oh no. Here, I'll line it up and change colors. How about that? TBD. I'm going to line up TBD under it. I'm going to put, it already is lined up, but I'm going to try to be, okay. I'm going to move my equals to the right. And what I'm going to do is I'm going to take this minus 10, and you can move it over there and it becomes plus 10. This one's still 0. So now I'm going to sit here, look at the BDs first. So I know I'm taking a little extra time to do this, but, and then there's a minus sign here, and it's a 4 over square root of 4 squared plus 2 squared. That's supposed to be a squared right there. And then there's a plus here, and I'm copying this one next, 2 over square root of 4 squared plus 2 squared. And then you got this one, which is a 2 over 6 squared plus 2 squared again. So I've got them lined up, right? There's my two equations. So really all I've done is copied them down, make them kind of lined up a little bit better. And then I'm going to put them into a matrix form. And there's something interesting that's going to come out of this matrix, and that's why I'm going to give myself a little bit of space up on top of it and to the right. Okay, so now I'll take, here, you know what? Here's what I'll do. I'll change back to red. I'm going to look at this. So the columns line up. T, B. Did I write that? Okay, let me correct something here. This is supposed to be a D. Okay, now TBD and TBC. These are the tensions. I'm going to go ahead and do the right-hand side of a 0 and a 10. Now I'm going to list the coefficients, which is this one, this one, this one, and that one. So put them in the right locations. 6 squared plus 2 squared. And then this one is minus 4 squared plus 2 squared. I think I made it large enough. I can fit this in all in here. Okay. 6 squared plus 2 squared. 2 over 2 squared. Now, here's what's so interesting. If I were to really look at this and step back, I would notice a pattern here, which this pattern exists every single time. Pattern number 1 here is this is the x, how would I say it, direction, listed this way. This, of course, is the y direction. So if I were to list them going vertically, what would I see? What I would see is kind of interesting. Here, I'll change it back to blue. I would see this is the x component of, let's say, I don't want to call it a base vector. I think in the book he was calling it and it's not a normal, but it's the unit. U, T, B, D. This is the y component of U, T, B, D. Believe it or not, this is not too surprising. The x component of the unit vector, which I guess I should list these as vectors. T, B, C. And this is y component of the unit. Yeah, I got to get U for unit. T, B, C. Now, and all I have to do is invert this. Here's why I do it this way, and I label it this way. And what you're going to find out is if I just go back and I list, I look at this, right? And I see that I have a rope from, say, B to D. I have another rope, which in my office, it's the same rope, but it's just tied in a knot from here. So if I were wanting to find, okay, I'm going to take a side issue and I'm going to say, I want to find the vector that goes from B to D. What would that be? Well, that would run 6I plus 2J. Real simple. If I want to find the vector that goes from B to C, it runs minus 4. Here's my 4. Running back to the left. Okay, so this is what I'm saying. Here's my vector R, B to D. This is my vector R, B to C. This is something he doesn't necessarily do in the book. He doesn't fill this part in, but if you fill it in, what you realize is working these problems become very methodical, and you can start seeing and thinking this particular way. 2J. So now that I've drawn these two, what I'm going to do is I'm going to bail and go to MATLAB now. Because the next thing I'm going to do, let's see, how do I make this go to the right? The next thing I'm going to do is I'm going to find my unit vector, R, B, D. And I'm going to find my unit vector, R, B, C, C. And I'm going to list these together to form that matrix that's way down there. And so let's do that real quick and go into MATLAB. Okay, so it seems like a weird way to do it until you realize that every single problem behaves the same way. And so R, B, D is equal to. Now I don't need all three dimensions, so I just need two. 6 and 2. R, B, C is equal to -4 and 2. This is a very strange workflow. Okay, so I have them all in there. Oh, well, that's not what I wanted to have happen, but 6 and 2 and 4 and 2. Okay, okay, give it back to me. Why is it not? Oh, it made it, okay. So now what I'm going to do is I'm going to find the unit vector. First of all, you know what I'm going to do? I'm going to do this. Unit vector of RBC is equal to RBC divided by the norm of RBC. This should end up with that vector, and we'll double check this if you want. The next one I need to do is BD. Okay. So now that I have all those, how do I list them? And it seems weird, but let's scroll down. It won't let me scroll down. Okay, this is weird. Maybe I will scroll down. Okay, now, let me move up just a touch more. Nope, that's not moving up, that's zooming in. But this right here, so now let's just pick that last one, RBD. Okay, so BD is the first column. Essentially, this column right there. So the first entry should be 6 over square root, 6 divided by square root of 6 squared plus 2 squared. Is that the first number? 9, 4, 8, 7. There it is right there. There it is right there. So in this essence, this first vector, it's listed as a 1 row by 2 columns, but I need that turned up on its side. And so if I were to create this matrix, how could I create that matrix to the left? In other words, let me go back here. So I want to call this something. Tell you what, let's do this. I haven't used green yet, so here I want to call this matrix something. It's a 2 by 2. I want to have a name for it. So I'm going to just call it K, big K matrix, capital K. How do I create that in MATLAB? Actually, it's not that hard. Okay, first of all, if I take that matrix, that vector, have it listed like that. People are moving around. Is it time to be done? Okay. Okay, but I want it to be listed that way. So that this little asterisk here is a transpose. So how would I do this K matrix? I would list it as a matrix that had this. Now, I may make a mistake. If I do, I'll have to change that, this comma to a semicolon. U, R, B, C. I didn't make a mistake. So here's what I was worried about doing this. Okay, this will make them all in a row. So that's not what I want. I want that one. So that, in fact, is the K matrix. Now, oh, go ahead.
In its simplified form.
Yeah, and it's completely, it's exactly, if you go in, why is it not, I'm moving up. I don't understand. What am I not doing here? Okay, so now, if you go look at this, those numbers, for example, this number is the 9487. 2 divided by the square root of 6 squared plus 2 squared, that's this number. Minus 4 divided by 4 squared plus 2 squared, that's this number. And 2 divided by 4 squared plus 2 squared, and that's this number. So in fact, it's exactly that. And so what I'll do on, you know what I'll do on Friday's stream, I'll take a picture of the thing I've got in my office. We'll work that exact problem. And I'll show you how to jump step over some of this other stuff so you can go straight to it and write the matrix and solve it just like that. But it turns out it works that same way exactly every single time. And it works exactly that same way in 3D too. And the issue is, when you get to 3D, it gets harrowing and confusing unless you do it this kind of way. And what's beautiful is you've already figured out how to do the base vectors. And I'm sorry, not base vectors, unit vectors. So you already figure out how to, if you got a rope tying two things, to figure out what the direction is from that rope. So if you already know that, then you know how to list it as a column. You just list it as a column. You just have to make sure if you're listing it as a column, you have two columns of them. They have to have the X components the first row and the Y components the second row. And that's it. That's all you need. So now if I'm going to work off the right-hand side, that's something we'll have to talk about. But I'll just say right-hand side is equal to 0 and a 10. So the thing is 10 pounds. And so now if I want to do this, I just do inverse of K times the right-hand side. There's my tensions. So it turns out, and here's something unique to look at, is that the tension of the rope is larger than the weight. And what we'll do on Friday is we'll play around with the numbers and we'll say, hey, what happens if in fact, instead of this dropping, okay, again, I don't know, it's behaving weird. Instead of this just dropping 2 foot, what would happen if I wanted that to drop like 1 foot or 6 inches? You'll obviously know what's going to happen is you're going to, if you tighten that rope, the weight's going to go up. So at what point do you pull that to the point where that rope snaps? So if you want it really, really tight, it might be ready to snap when you hang that on there. So the higher it is, the more that tension is going to be. And so we'll play with that because I'm actually doing that in the office. I mean, I'll show you the configuration I have. I have one light bar that goes like this. It's an LED light bar. 2 that go down, both shoot on a green screen behind me. And then I have 2 light bars with coverings over them that actually are back a little bit. So I have 5 of these light bars there. They're actually, you could say they're light bars, but they're actually not. They're actually garage lights I bought from Sam's. And they put out 5,000 looms, but anyway, what happens is you know, this is an entire set. This is essentially the statics course. Not all of it, but this is the meat of it in the sense that you want to know how to calculate the forces in members. In this case, the members are those ropes. Of course, you can't compress a rope because nothing happens, but if you need some sort of compression, it's going to have to be a bar or something. And this is a standard problem. Now you could do this, and this is pretty common. So maybe you have 2, and this is what I actually have. I have a weight here and a weight here. And so as it turns out, if this is a B, and C, and D, then really, whatever tension you have, like right here, is the same as you have right there. So once you find this one, you just copy it over and work your way through this one. So what I'm getting at is you work one problem all the way through, you get the tension AC and the tension CD. Once you got that, you've got this one, and then you go and work this next problem. So as many rings as you have, I mean, you could technically have, I mean, nobody's really gonna, you could do all sorts of stupid stuff like this. So you had this, I mean, I'm just making crap up now. So say you have this, and say you have something like that, where, and then there's a weight right there. I mean, you could have something like that. So if you have something like that, what you do is you work off of this one, solve all of it. If you solve all those, you've got this one and this one. Then maybe you work that one. Then you'll solve and get this one and this one. And then you work this one and get that, but that gives you this one. And then finally, so you can work your way through every single rope in that setup. And it's the only thing you can't do. And this is something, and I'll go ahead and lay this out in front of you because there's a part where he talks about this. Let's say I did this. So this is my configuration at my house, right? And then what I decide to do is attach another cable to the ceiling. Now, technically, you should be able to solve it, but not in this course. That would be in mechanics and materials. Here's why. Because you'll have an equation, let's say that's A, B, C, and D. So you won't know TAB, you won't know TAC, and you won't know TAD. Say this is still 10 pounds. But you only have two equations. You have your X equation, which would be sum of the forces in the X, sum of the forces in the Y. You only have two equations, meaning you don't have enough to solve this. So how could you solve that? If you realize that this is a piece of metal, and this is a rubber band that's very soft, and this is a piece of metal, then you'll realize if you had those properties, you could realize that, A, the rubber band's going to stretch a lot for a force. The steel is not. And so you would, think of it as this. F is equal to Kx. And essentially, X or delta, depending on which way you did this. And you've seen these springs before, haven't you? That's seen. So if you had that, then not only can you find the tension, but you could find how much the deflection of this thing was. So when you start doing that, you start using this as a springs, you realize, okay, I can not only just find the three tensions, I can also find the deflections of the point in that. And that's the other equations. So there are other equations that are down here.
That you go over in mechanics and materials.
Yeah, that's in mechanics and materials. So, but until that point, what they say in this course is they say this is statically indeterminate. That means you can't determine it with just statics. That doesn't mean it's physically undeterminable. It means it's statically undeterminable. So when you get, off in that, and we could look at that later. I could give you if I knew this was a spring stiffness of 400 and this was 100 and this was 400, say, feet per pound or something, some other units, then we could actually go through that and figure out what it would be. It wouldn't be that hard to do. Now, in mechanics and materials, what they do is introduce you to the modulus of elasticity. And that is the fact that, steel is modulus, roughly, 330 times 10 to the 6 pounds per PSI. Well, that's okay. It's a stiff material. I have no idea what a rubber band is, but it's probably in the neighborhood of a couple hundred. I just don't know. I know aluminum is 3 times more flexible than steel is. So its modulus is around 10 times 10 to the 6. And titanium is close to aluminum, but I don't remember if it's a little above it or a little below it. So it's flexible as well. So, those are things that when you start considering this, you're starting to look at that flexibility. And that's where this moves out of statically indeterminate. So when you hear this term and you read it in a book, don't panic and say, these are undeterminable. They are determinable, but not from the material in this course. So, and that's something that often people walk away with, is they think they're not solvable, but they are. So I guess we're done. Let me unroll all this. And next time I'll take a picture. I'll put the picture up there. I'll even measure, because I have this electronic measuring thing, so I can measure all the distances. Do one lamp. I'll do one, and then I'll do two. And I'll measure exactly where they are in the room and exactly the tension in those cables. And I think I have a scale that's fairly accurate. I can measure the weight of the light bulbs or the light fixtures. So anyway, we'll call it good. So I guess I got to unfurl all this. Okay, so get rid of MATLAB. Now, before I do that, I have to stop this.